I ask everybody except of the speaker to mute their microphones. All right, so we are happy to have Umut, I'll try Varolgunes, from Stanford, who will speak about non-archimedean mirrors of symplectic cluster manifolds. Thank you, Umut. Go ahead.
Okay, so I'll share my tablet screen. Okay, so I hope it's visible. Yeah, so I have some plan here, which is too long to be of any use. And I have some diagrams, which are also going to be useless at this point. But I just want to explain in words what my plan is for the talk. So I'm going to talk about certain four-dimensional open symplectic manifolds, which I'll call cluster symplectic manifolds, and I'll try to justify why I'm calling them cluster symplectic manifolds. These are not new manifolds that I invented. I'll tell you what might be new. And I will represent these symplectic manifolds by certain combinatorial pictures, which I will call Eigenray diagrams. So I'll introduce somehow these notions and maybe justify a little bit why I call them cluster manifolds. And then I will talk about certain Floer theoretic invariant that I'm gonna use to construct mirrors of these so D-side mirrors of these symplectic manifolds. And this will rely on a certain locality theorem. So technically speaking, this is probably the biggest contribution of our work. So I'll say this, but this is joint work with Yoel Groman. And I would like to explain some local computations on some models that actually somehow capture all the necessary computations by using general principles. And I will construct an algebraic mirror. And I will then construct also, I will briefly explain how one would construct an analytic mirror, which is supposedly the analytification of the algebraic mirror. Okay, so all of this is joint work with Yoel Groman. Okay, so let me begin. So I want to first, so the symplectic side of the story will rely a lot on integral affine manifolds, and somehow that's where I'm going to start with kind of concretely constructing symplectic manifolds. So first I need, so I hope everyone is kind of familiar with what integral affine manifolds are. So these are topological spaces with some atlas where the transition functions are elements of semi-direct product of translations and linear elements of GL and Z as GL and Z. You can also require them to be elements of SL and Z. Okay, but so let me, somehow if you want to work in a kind of in some meaningful generality in symplectic geometry, you have to allow certain singularities. So I'm going to allow very certain special kinds of singularities in my integral affine structures, which I'm going to introduce now. So we take let me choose this. So I'm going to define an integral affine structure on R2 minus the origin. And this integral affine structure is obtained by, so you make a cut along the positive real axis of R2 minus the origin. And you also remove, let's say, an infinite strip, as I indicated with the shaded lines here. And you reglue that infinite strip into the R2 minus the branch line differently in the two regions, and the two connected components that are in the intersection of these two charts. In the one chart, so here you just use identity, and here you use this shear matrix, 1, 1K. Okay, and so this defines an integral affine structure. And in this integral affine structure, depending on what K is, the straight lines look like this as you cross the, so if you know, the lines that naively look broken, they're actually not broken in this integral affine structure. They're straight lines. And so I will also denote by bk. So these integral affine manifolds I will denote by bk. And these integral affine manifolds admit a topological compactification to R2. And I will just denote them by bk bar. Okay, so a nodal integral affine manifold then is a topological manifold B with some specified nodes and an integral affine structure in the complement of the nodes, such that the punctured neighborhood of all these nodes are isomorphic to one of these models that I just defined. Okay. So this is not going to be a problem for us, so because the nodal integral affine manifolds that I'm going to talk about will automatically be of this form. But if you were presented with some random guy, you could just this kind of local model. The fact that you're isomorphic to local model is just equivalent to computing the affine monodromy, showing that it is given by this matrix here. Okay. So in practice, you could check that by doing that. So now the relation to symplectic geometries is that if you're given such a nodal integral affine manifold, you can canonically construct a symplectic manifold from it. So so the complement of the nodes where I actually do have an integral affine structure, I can construct this symplectic manifold by just taking the cotangent bundle and modding out by the lattice in the cotangent fibers that's defined by the integral affine structure. So this is good, but it's missing some fibers, and in order to fill those fibers, you have to find some actual symplectic manifolds which admit Lagrangian fibrations whose bases look like BK, and then you have to glue them in. And you have to work a little bit for it, but you can show that the resulting symplectic manifold is actually independent of any of the choices that you might make in this process.
Are you thinking about compact symplectic manifolds?
No,
or?
no.
Okay, so will you have in addition conditions at infinity?
I will have conditions at infinity. Okay. Yes. So I'm not going to be able to do flirt here with just in this level of generality. That's part of the point. Yes, I will come to it.
Can I ask? So the fiber you glue in, is it has a K pinches, or
yes,
it
yes.
has just one? I mean, is
yes.
that the only way to do it? So you cannot like some of them combine together, so that you want them to be K distinct pinches?
Yes, combining together makes the manifolds singular, I think.
Yes.
And I mean, I don't know how to do symplectic geometry with those, at least.
Okay.
Yeah, but there are models with singular, where you combine some of those focus singularities and get singular manifolds, but I don't know how to work with them. Okay, so this symplectic manifold, almost by construction, admits a Lagrangian fibration. So the same topological manifold, this nodal integral affine manifold. And this, again, by construction, it induces the given integral affine structure. If you look at if you just look at the integral affine structure induced by Arnold-Devaux theorem, you will see that it gives you the, again, this is trivial, the given integral affine structure would be smooth. And this Lagrangian fibration up to, fiber-wise equivalence is not exactly unique. There are some choices here, but these choices are contractible, and it's very controlled how you make these choices. So this choice, in the end, for practical purposes, doesn't really matter, but it's something to keep in mind. I won't be very precise about that. Okay, so let me introduce also. So this manifold that I obtained from B, where B is an nodal integral affine manifold, I called it MB. And let me also introduce the notation MK for the integral affine manifold B bar K. So if I take any of these models that I introduced, those in particular give me symplectic manifolds, I'll call them MK. Okay, so there is this for nodal integral affine manifolds, there's this operation called the nodal slide symplectomorphism. So let me quickly try to explain what that is. So now if you consider, so this B and B tilde are just subsets of this this picture that I have here. So let's so those open sets, they are just open sets of let me just maybe say it like that. So this is a subset of BK bar, and this B tilde is not a subset of BK bar, but it's a subset of BK bar with this node that I make moved towards the right along the ray that I chose, the branch ray that I chose, by some arbitrary amount. Okay, so that also defines an integral affine manifold. And I choose this open subset. So these two open subsets are naively identified with each other. Okay, so they're just somehow, if you just look at R2 and forget about everything, they're the same subset, but they're equipped with different singular integral affine structures. But it's very important that I move it only along that branch. Then, so both of these guys give me symplectic manifolds by the construction that I just outlined. But these symplectic manifolds a priori are different. So what I'm claiming is that they're not actually different. They're symplectomorphic by a symplectomorphism that's equal to the naive identification outside of an arbitrarily small neighborhood of the ray along which, the line segment along which my node moved. Okay. So this is some Moser argument. You have these two guys are clearly diffeomorphic to each other. You push, you pull back one of the symplectic forms to the other. So you're talking about two symplectic forms on the same manifold. You do some kind of Moser trick to construct the symplectomorphism. But the point is that this is kind of compactly supported. And the implication of being compactly supported is that you can implant this in more global situations. Okay, so I will call these nodal slide symplectomorphisms. Okay, so now one of the key definitions is this definition of an Eigenray diagram. It's a simple definition, so it's just a disjoint union of rays with rational slope inside R2, where I'm, when I say rational, I'm talking about the standard integral affine structure on R2 with the lattice Z2 inside. And these are sometimes called Symington cuts in the literature, even though it's also not the most commonly used. So I might call them Symington cuts, but more universally they're known as eigenrays of these nodes. Okay, so now given such a guy, also I didn't explain, so it's not just rays. So in addition, even though I'm not going to actually talk about these, you could allow for nodes, more than one node along each ray, and you can also, this I will allow. You can also you also have to specify what the k from my local models are for each of the nodes. So this is purely combinatorial data, and I will make it even more combinatorial later. So then if I'm given an Eigenray diagram, which is some diagram like this on the plane, I can construct a nodal integral affine manifold. So this construction is exactly the same construction as the local models because these rays are disjoint. You have to be, slightly careful about dealing with multiple nodes on the same ray, but you can do it. It's not much harder. And since I obtained a nodal integral affine manifold, I also obtain a symplectic manifold by my general construction. Okay, so now, even though one could deal with, Eigenray diagrams of this generality and the induced symplectic manifolds, I'll make a simplification, and I'll assume that there are no more nodes than the minimum allowed on each ray. So I'm actually not going to have these guys. I don't want that generality. And I also will not allow I will not allow rays to be parallel to each other. So this I will also not allow. So for every direction, I have just one ray. And finally, I will also assume that all the numbers are positive. Okay, so I will not allow negative k's. So, bk and b minus k are integral affine isomorphic to each other, but this is of course not true globally. Globally, if you have more than one node, then having one of them +5 or -5 will change depending on, will change what this integral Fi manifold is, depending on what the others are. So globally it's a choice, but I'm making a simplification here. Okay, so now I will say, I want to say that an Eigenray diagram, a node in an Eigenray diagram is a mutable position if the ray that extends to the other side of the Eigenray, so I have this Eigenray and this Eigenray in my picture, this one and this one. I look at the other side of this, and if that ray does not intersect any of the other eigenrays, then I will call this node a node in mutable position. Okay, so in this example, in this picture that I have here, it's not in, so this node that I circled is not in mutable position because it intersects. But in order to make it in mutable position, what I can do is I can move this guy, the ray that it intersects, along. So, you know, what I use in my description of nodal slide symplectomorphism. So this operation is called either moving of the worms or nodal slide. So you might have heard either of those. But after you do that, then this node now becomes a mutable position. And by just sliding the other nodes arbitrarily, arbitrarily far away along their given eigenrays, you can put every node into mutable position. And once you do that, when a node becomes in mutable position, you can apply a branch move at that node. So that means that, so let me just try to say it with this example. So if you start with this picture, for example, so this guy, I think I'm trying to make a branch move at this point. So I see that it doesn't, it's not in mutable position. So I move this guy down. So I obtain this picture now. And then I make a branch move, which means that I, instead of choosing this eigenray, I choose the eigenray on the other side. But now I actually have to apply a shear on one side of this diagram. So all the eigenrays on one side of this line change by a shear, by whatever k is on that node. One side stays the same, the other side changes by shear with multiplicity k. And the point is that this does not change the symplectic manifold that you're describing. It again gives rise to the same symplectic manifold. And this operation recently was used by Vienna, construct exotic tori in CP2. But this operation was, of course, known even before that. And I will say, even though symplectic manifold doesn't change, something changes when you do this, and I'll get to how to measure, like how I will think of what changes. Okay. Okay, so an eigenray diagram. So this part is about how to relate the eigenray diagram and the symplectic manifold that's obtained by to cluster varieties and things that come up in that context. So I can think of an eigenray diagram as seed data. So throughout this discussion by capital I will denote the set of nodes. Okay, so I have some eigenray diagram here. So I denote, along each eigenray, I have primitive vector n. So in the ith eigenray, I will have the integral primitive vector ni. And I also have this multiplicity ki. And I also have the locations of the nodes of the eigenrays. And somehow, because of this nodal slide symplectomorphism, I will not really distinguish between a node that starts here and a node that starts here. But I'll be more precise about that. So now, here's a slightly kind of those matrices that I introduced, those shear matrices. They can be thought of in a slightly more invariant way. So I can equip Z2 with the skew symmetric linear form given by just determinant. And this skew symmetric bilinear form only depends on the orientation of Z2. Doesn't depend on the basis. And using this, so just one comment that I'll get back to is using this skew symmetric form on Z2 and all these ni's, I can send the ith basis vector of this into the ith primitive vector. and pull back the skew symmetric form to this larger lattice. Okay, and that's the only reason why I mentioned that is because it will come up in how I relate this to cluster varieties, and that's also a known construction. So the matrices can be more invariantly expressed by this linear transformation. So any vector goes to k times, where k is the same k, the multiplicity, and n is the integral, n is the primitive vector along the eigenray. So somehow restating more or less the same thing. So the data of an eigenray is a bunch of vectors in this Z2 with the determinate skew symmetric form and some numbers. Okay, so these numbers are what are those numbers? So each of these locations of the nodes, I can those give me just back another, for each node I have another vector in my I have another vector in my Z2. Oh, sorry, not Z2. That's in R2. So this time, the locations of these nodes they don't have to be at integral point. But so this choice of where this node is, as I mentioned, it only matters up to moving it on its eigenray. So I can measure kind of how far away. So it's only kind of the horizontal. The coordinate is what matters. So you can talk about all this in coordinate invariant terms, but just to give you the idea. And so that's just one number that's determined by one number. And that number I can encode as just that vector, vi, which tells you where the point is, and the primitive vector, and just apply omega to that. So if, for example, if it looked like this, then my vi will be in the direction of ni here, so the number will be 0. Okay, because it's skew symmetric. Okay, and so these alpha i's, so strictly speaking, the alpha i's will only matter up to changing all of the vectors by an overall vector. So the choice of the origin actually doesn't matter for this, like the symplectic manifold doesn't really see the origin. So if you move everything by the same vector, then somehow the symplectic manifold doesn't change. So you should really think of these numbers up to some modding out by a two-dimensional linear space. So the real number of parameters is not the number of elements in I, but the number of elements in I minus 2. Okay, and what do these numbers alpha I measure in terms of the symplectic manifold? Well, first of all, they measure the failure of the eigenrays to pass through the origin. And this is explicitly related to the exactness of the symplectic form on MR. So if the symplectic form that you obtain in MR, so you can try to construct a primitive of the symplectic form, and you will be able to, using the geometry of the base, and you will succeed only if all of these alpha i's are 0, up to this R2 discrepancy that I mentioned. Okay, so this is a measure, this numbers are a measure of non-exactness, and I think this is the part that's not really covered in a systematic way in the literature from the symplectic viewpoint, from the symplectic side. Okay, so this seed data is exactly what one uses to construct this cluster varieties after kind of pulling the skew symmetric form back to Zi by the map that I described. And these are rank 2 cluster varieties. So I don't think this rank 2 notation is necessarily standard, but it just says that the skew symmetric form that you use to define your cluster variety has rank 2. Generally has rank 2. Okay, so what is my conjecture? So you can construct this this cluster variety. This cluster variety comes with a map to some algebraic torus of the 2 dimensions less, and a complex 2 dimensions less. And the fiber above the identity is an exact symplectic, so it has a holomorphic symplectic structure. This cluster X variety has a Poisson structure. So this is one of the leaves of that Poisson structure. So this is an actual holomorphic symplectic manifold, that fiber. And I claim that that fiber should be up to filling some holes, should be MR, should be the manifold that I described. So I'm able to define two symplectic manifolds, one using the Eigenray diagram, and then I turn it into a seed, and I define this kind of cluster variety in the usual way. I take the fiber, the symplectic leaf above the identity, and that also comes with a symplectic structure. So it comes with a holomorphic symplectic structure. But I take the imaginary part. It's important to take the imaginary part of the holomorphic symplectic form. And I claim that I conjecture that these are the same symplectic manifold up to some holes.
So what happened if you take real part of the symplectic?
So the real part, that one doesn't have a Lagrangian fibration, Lagrangian torus fibration.
You should rotate the complex structure.
Yes, yes, yes.
Okay, and also I remember that in this Fock and Goncharov business, they have X varieties, X like yours, and A variety. And
yeah, yeah. So I mean, there is a but I think, so I will say something about this, but at least up to now, I'm only mentioning this kind of exact part. So I'm only mentioning the fiber above E. So I think this admits the description using both of them. So either you take the fiber above identity, like the symplectic leaf of CR, or you use this torus acting, there's a torus acting on the A variety, and you do kind of symplectic reduction with that, and those two, if you take the kind of right fiber above the moment map, I think they give exactly the same symplectic manifold.
Okay.
So at this point, I don't think you see the difference. I don't think anything I will say will, yeah, I don't know. There are parts that I don't understand, which I'll get to. Okay, so by construction, this UR, this cluster variety, but it's not the full cluster variety, it's just this fiber, this symplectic leaf, that almost has a covering by C star square charts. And in these C star square charts, so like there's this missing fibers thing, that missing points, there are some holes to be completed. I'll say something about that, but that's why I say almost covering. So there are some C star square charts, and in those charts, in some coordinates in the C star square, the holomorphic symplectic form looks like this, the standard log form. And these charts are glued to each other by maps of this form. This is a concrete way. So for me, I don't know why people do this. Maybe I'm just missing, don't do this a lot. I don't know. I might be just missing something. What is this? So instead of thinking of these rational maps, I find that it's better to think that there exists some variety, yk, for every k, which admits these two dense inclusions of the C star square torus. And if you just look at the map, so these are dense, but they don't have the same image. So they, their image differs on some codimension one locus, and that induces a rational map between these two C star squares. And you can choose this yk and the embeddings in such a way that the induced rational map is just this cluster transformation. So, for example, if k is equal to 1, so if k is y1 would be just C2 minus a conic. So everyone knows this has two C star square charts, and the C star square embeds into this in two explicit maps. And if you look at the induced rational map, it should be in some coordinates equal to the cluster transformation. This is the cluster variety with two charts. And if you want the higher, if you want the other case, what you want to mod this out by some action of zk and take some resolution. So it's like an resolution of an singularity, but you have to remove the conic again. Okay, so but using this one has the advantage that now I don't. So normally when I just glue these two C star square charts, I'm missing something from this yk. But I want to actually think of them as kind of gluing into this yk. So I don't want it to miss those holes. Okay. So now if you consider the imaginary part of this log form on C star square charts, you see that it's the standard form on T star T2. It's a tautological, the standard cotangent bundle form. And the standard cotangent form is just N0. Okay. So now the sub-conjecture of the vague conjecture that I made about UR and MR being the same is that I claim that these local models are the same. And I know that this is true for k equals 1, 0, and 1. And then I mean, yeah, I think it's true for all k. And then I will extend, so you also have to show, if you want to show what I'm claiming, you also have to show that these isomorphisms are compatible with kind of gluing. So in order to show that, I will tell you that there exists some embedding of M0 into all MKs. This is obtained by moving the worm to infinity. And there's also this inclusion of Y0, which is just C star squared, so I choose one of them. Either of, for both of them, there's two choices, but I choose one of them compatibly. And this diagram should commute up to Hamiltonian isotopy. Okay, so this is a slightly less vague form of the conjecture. So, but upshot is that to me, I'm thinking of UR as just somehow I'm gluing this MKs along M0s. Okay, so if you think about the cluster, if the tree, I don't know, maybe this is called cluster tree, I forgot. If you think about this tree, so each of the vertices of the tree have this kind of M0, a copy of T star T2 inside my symplectic manifold. And each of these edges correspond to some rational map, which I'm actually thinking of as this kind of compact, not compact, but this holes-filled version of the gluing. And to me, actually, it's better to think of this diagram as you have these guys, and you glue them along M0s. Okay, and this is, I don't need to actually use this conjectural picture. I will show you that I can actually construct exactly this diagram if I'm given an MR. So if I just think of an Eigenray diagram and I think of the symplectic manifold, then by sliding nodes to infinity and doing Vienna mutations as I described, I can just construct a cluster tree like this. Okay. So now, as I said, I somehow, so this U guy, this is exact. And there are ways to deform this. So in the Eigenray diagram picture, you kind of move this worms in the directions that are complementary to the Eigenray direction to deform. But in this cluster picture, there are ways to deform as well. I just don't know exactly how they correspond to this movement of the nodes in complementary directions. So we can look at other fibers, other symplectic leaves of cluster variety. Can do symplectic reduction for different values in the moment map. I don't really understand how this will work. But you can slightly more concretely, you can also add into your cluster transformations, you can add some elements of C star. Okay. And these all deform somehow. I'm just thinking about the symplectic structure. These all deform the symplectic structure in some way, and they should correspond to using non-zero alpha i's, which were this kind of failure of all eigenrays to pass through the origin. Okay, so that was a long digression into cluster. So that's why I'm going to be calling these things symplectic cluster manifolds. So any symplectic manifold that's symplectomorphic to MR for some eigenray diagram, I call symplectic cluster manifold. Okay, and when I have a symplectomorphism, when I choose a symplectomorphism like this, I automatically obtain a symplectic embedding of standard T star T2 inside my manifold. And I obtain automatically an embedding of MKI for every node, where the node has multiplicity Ki. And this is all by sliding nodes to infinity. So let me show you a picture. So I hope you can see it. So now here's my D0. So this is my T star T2. Yeah, and I will kind of embed T star T2 kind of slowly. I will take an exhaustion and I will embed each piece of the exhaustion and then extend the next piece, extend to the next piece, etc. And the way I do it is I start, I see some nodes here. I see some nodes, for example, they're here in the beginning. Well, I look at this piece of the exhaustion. I see if it doesn't fit, then I move some of these nodes. so that now I can just like naively embed that here. And then if I want to embed a bigger one, then I move them even more, and then I embed that here. But because of this nature of this nodal slide symplectomorphisms, they're only supported here. So they don't actually change the previous, they don't actually change what you did with the previous embeddings. Okay, so this way you can embed the entirety of this T star T2. But if you also keep one of the nodes fixed and just move all the rest, then you can also embed other models. So this, you can embed just MKI, just fixing this node here and moving all the rest to infinity. You can also do this embeddings by choosing some kind of, there is also a Liouville flow argument that gives you these embeddings. But I'll omit that. Okay, so now the images of these embeddings. So remember that for each node, I get a symplectic embedding from the full model, full local model MKI into MR, and the intersections of each of those, the intersections of any two of these embeddings, the images of these embeddings are just along the image of the embedding of T star T2. Okay, so you can see that like the intersection. So if you look at this, well, okay, maybe I will just leave you to think about that because it will make me, maybe I take questions. Okay. Okay, so now, so that gives me what I will call an R-adapted cover of MR by this kind of MKIs intersecting along M0. Okay, and these embeddings are also standard. They're just kind of for if you had just MKI with just one singularity, you could push that one to infinity and get an embedding of T star T2 into MKI. And they all look like that up to some change of basis and translation. Okay, and using Vienna mutations now, I can also obtain another isomorphisms of M with different Eigenray diagram, with another Eigenray diagram. And then, I get all of these embeddings for that diagram as well. And you'll see that this procedure, as you keep doing it, it just reconstructs for you the cluster tree. Okay, so maybe I'll skip this portion. So this portion I was, so there's the way people generally equip this manifold UR that I talked about with a symplectic structure is by finding a toric model for them. And on that toric model, they find a Kähler form. And the toric model involves some blowups. So in the end, you're supposed to do this kind of mysterious inflation procedure that I've never seen it written anywhere. So this is, if you want, you can think of this construction of a symplectic structure as a replacement for that. So maybe I'll show you just one picture. So for example, if you wanted to think about the symplectic structure that you get by taking a CP2 and doing a non-toric blowup at this divisor, and instead of removing this triangle, as people usually do, and kind of adding this node at the tip, you do a branch move, and you glue this here, but you make a branch move here, and instead of inflation, you just ignore the boundary. So there is just no boundary. Okay, and this. So doing this somehow, like if you do this blow up procedure, somehow these parameters that I talked about, these alpha i's, they're very hard to keep track of, because in symplectic geometry, doing blow-ups at different points is not necessary. So the blow-up doesn't really happen at a point in symplectic geometry. There's not really a point that you choose. You remove some ball and you do boundary reduction in a neighborhood of that. So it has a completely different nature. So this kind of the parameter, if you think about the blow up, is kind of the size of the ball that you're that you're removing. But this is a very complicated thing to keep track of. So I don't actually know how to carry that through after inflation. Okay, and I also want to claim that this kind of anything that you can draw as a toric diagram, in fact, you can also allow non-maximal boundary, if you know what that is, and kind of take the complement of the strict transform of the toric boundary, that you can equip that differential smooth manifold with an Eigenray diagram type symplectic structure. Okay, so these are the symplectic manifolds that I'm considering. So these MRs, and they admit these R-adapted covers. And I want to use these R-adapted covers to construct a mirror. Okay, so the Floer theoretic, so this is going to be a Floer theoretic construction, and somehow the most, this Floer theoretic construction is called it's called relative symplectic cohomology, and it can be defined on any. So this is a algebra over the Novikov field, let's say, that can be defined for any compact set of a geometrically bounded symplectic manifold. Okay, so it's important that it's geometrically bounded. And so one example of a geometrically bounded symplectic manifold is this MR. So you can construct some some almost complex structure on MR using its Eigenray diagram that shows you that this manifold is geometrically bounded. So you can use, let's say, monotonicity techniques to get C0 bounds, to get chromo compactness. Okay, so it's defined for any compact subset. It's an algebra over the Novikov field, where kind of Novikov field is this guy for me. And this invariant is relatively recent in this generality, and it exists in works of different people: Seidel, McLean, Venkatesh, Groman, and also myself. And it's defined using this kind of, for every compact set, you take this kind of cofinal sequence of functions, these functions that converge for every point inside K, the values of the functions at that point should converge to 0, and outside K, they should converge to infinity. And you kind of apply the Hamiltonian, you look at the Hamiltonian Floer theory of these functions, so that gives you a diagram of chain complexes. And then you take the telescope of that homotopy colimit of that diagram, and then you apply a completion procedure, which is important. So this completion, if you know about it, corresponds to these action cutoffs that earlier invariants will do. I don't have time to give details on this, but it's some construction of it. Yeah, I will just have to. You will just have to. If you've never heard of it, you can ask me about it after the talk. But it's some invariant, and I'll give you some results of some computations about it. So now, if you use an open set, you can take an exhaustion of this open set by compact sets and define an invariant as inverse limit. And if your open subset, as a special case, if your open subset is the whole manifold M, then you obtain a symplectomorphism invariant by this procedure. So you take the inverse limit of exhaustion of your manifold, and you take the inverse limit of the relative cohomology groups associated to each of those compact sets. Okay, so now this part is about locality. So at least we want to identify cases in which, if you have a subset, let's say an open subset of a geometrically bounded subset, let's say this U itself is geometrically bounded. So you can define SHU, but you can also define SHMU. So you can think of U, as a symplectic manifold itself and think about its invariance. Or you can think of U as a subset of M and think about its invariance. And I'm going to tell you that in some cases, these two things are the same. Actually, U is local. U is doesn't see that U is a submanifold as a subset of M. So in order for this to happen, there is some extra condition on U that we have to assume. That it also has to be what we call this, what Yoel calls dissipative, Yoel Groman. So this is his expertise. So if U is a conical at infinity, meaning that it looks like the positive symplectization of a contact manifold, then this property is satisfied, for example. But it's satisfied more generally than that. Like for example, actually all of these MRs that they are also dissipated. They also satisfy this property. So this dissipativity has to do with admitting a Hamiltonian, which outside of a compact sets kind of moves every point by just a little bit. So for example, there are no periodic orbits there are no fixed points of, if you think about the Hamiltonian geomorphism, there are no fixed points, and every point moves a certain amount. This is used to get kind of some bounds on energies of Floer trajectories that leave, that go very far away in your open manifold. Okay, so let me just give you a picture about how, like, what kind of U's can satisfy this property. Again, this is in the context of Liouville, this Liouville geometry, but it's more general, the result itself. So if you take, for example, this symplectic manifold M, so it's some kind of a punctured torus, and you take some kind of subset D here, and you take a Liouville structure that looks like this. Here it looks like the symplectization. And then you just flow this compact domain as far as you can. So then the only points that it misses are these kind of, these connection points between two different, this kind of separatrix points. So this red region. Let me erase these guys now so that they don't complicate. So U is very large. So U is kind of, the difference between M and U is this codimension 2 subset given by the union of descending manifolds for the for a plurisubharmonic function. Okay, anyway, so this is some picture that you can keep in mind. So these U's are quite large, and of course the U's that I will have in my construction is these embeddings of MKIs into MR or M0 into MR. Okay, so the theorem first is that if you have a compact subset that's contained in such a geometrically bounded and dissipative open subset, then there's a canonical isomorphism like this. So it doesn't matter if you compute the invariant of K as a subset of U or as a subset of N. This is the first locality result. And these maps are compatible with restriction maps. They're compatible with various maps that you can you have in this framework. And also, as a corollary of the statement for compact manifolds, you also obtain that this statement is true. So if you just look at the open set itself, then there's it's the statement that I started with. So if you just compute the symplectomorphism invariant SHUU, it's the same as computing the invariant of U as a subset of N. And this has a Hamiltonian isotopy invariance property, these isomorphisms that I will not state. So I want to apply these statements to the embeddings M0 and MKI into MR. Okay. So let me do an example computation without actually doing the computation, just the result. So if I consider this kind of simplest model, just no singularities, T star T2 R2. So I mean, I will call this Conceivit-Zeuvelmann shift because I think they are the first ones who discussed this in the context of mirror symmetry, but people have probably known about it earlier than that. So I want to define a sheaf on R2. So this is going to be a sheaf with respect to some kind of Grothendieck topology, but let me just tell you what the sections of this sheaf are. For a convex polygon P inside R2, you have this kind of convergent formal power series. So these are power series that look like this. with coefficients from the Novikov field, such that this, if you look at kind of the valuation, so if you look at kind of this point, that point gives you a pair of real numbers, and you can input that pair of numbers into, these expressions, kind of well, I think if you know about this, you already know what I'm talking about, and if you don't, it will take me a long time. So it's just some kind of you just take these formal power series and you acquire some kind of convergence, but this convergence only depends. So you kind of apply. Yeah, I don't know how else to explain it. So it's some kind of tropicalization of, not some kind of exactly tropicalization of these polynomials. So that thing has to converge. Okay, so if maybe there's anyone who needs a particular explanation at this point, maybe I can do that. Okay. Okay, so the result of the computation is that if you look at the zeroth component of this invariant in the pre-image of that polygon inside my symplectic manifold, you will see that you see that it's canonically isomorphic to this convergent power series. Okay, so this is the computation, and the way to prove this computation is to use this computation of Viterbo symplectic cohomology, and realize that both sides in this special case can be defined as completions with respect to certain norms defined by P on the two sides of this isomorphism, this Viterbo isomorphism, and showing that this isomorphism actually respects these norms that are defined by P. So they're both completions, and they're both completions that are defined by this polygon, and you can just check that the norms are actually intertwined by this isomorphism. Okay, so the corollary of this computation is that if you look at SH0, M0, M0, this is isomorphic to the algebra of entire functions on the non-Archimedean torus. Okay. And so now let me give you another, so this will be a local computation about M1. That was the computation for M0. So M1, this has just one singularity, and this Eigenray. And I want to consider a convex polygon, let's say, that lies above the Eigenray diagram. So now I can move this Eigenray to infinity in this given direction. And by doing that, I obtain a locality isomorphism. So here, when I move it, I can think of this pi inverse P as a subset of M0. So that gives me an isomorphism, and I had already computed that this guy is isomorphic to this Concevic-Zoibelman functions. Okay, but I can also make a branch cut and choose this guy, and I have to maybe change this depending on what side it looks like. But if I change the branch and obtain the other embedding that I can get by of M0 into M1, I get another locality isomorphism. And these isomorphisms induce for me a map between these two Concevic-Zoibelman function rings. And this map is not trivial. And this map is exactly given by the cluster transformation. So this is some kind of remnant of the rational map between two tori. And you look at analytification and you look at certain subsets that are in the intersection of the analytifications of the charts. And so why do I get something non-trivial? So this is a manifestation of wall crossing, but it's kind of a different way to measure it than the ones existing in the literature, because I'm not looking at Lagrangians. I'm not looking at holomorphic disks with boundary on Lagrangians. So what's happening is that so both of these locality isomorphisms rely on computing this invariant using two very special, almost complex structures, both using the geometric boundedness of the given open subset. I have to choose J such this is also similar to doing some kind of next stretching. I'm choosing a J that's kind of very infinite at the bound, as I try to leave this open subset, the J is kind of as if it's I'm inside an infinite cone, so I cannot leave this region without spending infinite energy. But because I have to make these two different choices, then in order to relate them, I have to choose a one-parameter family of J's between them. And if I look at that one-parameter family of J's, you will see, well, if someone actually is able to do that computation, they will see that at least one of these J's is not regular. And that regular for the Floer theory that I'm doing. So there are some kind of accidental solutions, for example, contributions to the differential. So the differential, you're normally supposed to count this, index 1 things, but here you will have to count some index minus 1 things as well, because you're considering a family. So index, depending on whether you mod out or not. Okay, so one less dimension than what you would normally consider. And that irregular J will kind of make this map non-trivial. So this is pretty hard to compute. So we don't actually compute that. But what we do is we kind of that's a whole kind of another half an hour itself. But it doesn't actually use any direct computations. It just uses kind of compatibility between definitions and the computation of the T star T2 and the polygons in the base of that. Okay, so now since I don't have a lot of time, let me just switch to kind of go quickly. So let me just, I'm gonna have to skip the probably the analytic construction. So the Kontsevich-Zeuvelmann construction of this this convergent functions on a base actually extend to the B1 as well. So above B1, there's this non-Archimedean analytification of this non-Archimedean affine variety, and it admits a continuous map to the base B1 bar. And Kontsevich and Zeuvelmann explicitly computed this sheaf on the base. So now if I look at the kind of SH0 of pre-images of convex polygons in B1 bar now, I see that that's also given by the Kontsevich-Zeuvelmann sheaf, but now on that base. Okay, so this tells you, for example, that if you look at SH0 M11, that's entire functions on this analytic space. Okay, and let me just finish with the construction of the algebraic mirror. So you start with your MR, and being in the form MR, that already gives me this R adapted cover so now let's say for simplicity, K I equals 1. You can ask me about other Ks if you're interested. So I take this cover by M1s, and so let's call the image of the ith M1 Vi and their intersection, which is the image of M0 W. So I obtain this kind of V1, V2, etc., and all of them contain W, and I apply my SH0 MR functor to this. So I obtain a diagram of algebras. So now these maps are restriction maps. And the previous results that I mentioned more or less kind of tell you that this diagram that I'm seeing here is isomorphic to just after applying these functions. Let me just, so you consider this diagram where y0 is the non-Archimedean torus, and y1 is kind of the non-Archimedean version of this variety with two cluster charts. And each map in this diagram is not exactly of the form that I see in the cluster world. It's not exactly the standard. It's not exactly the base change of the standard map from C working over the complex numbers. but it also has this kind of translational component. So you translate a little bit and then you map it in with the standard thing. And this diagram, I know, defines a cluster manifold. So this covers, I think, actually the cluster manifold UR, if all of this was over C. But it's not over C, it's just over the non-Archimedean field. And then, so I just constructed this kind of cluster variety from kind of symplectic Floer theoretic data. And the cluster variety over the Novikov field with this kind of extra translation thing, which will result in just adding a T to, so there was this place that I could modify cluster transformation. There I have to add a T to the alpha. So it's Z2 goes to Z1 times, Z2 goes to Z2 times 1 plus T to the alpha Z1. And this is supposed to be the mirror. And justify that this is actually the mirror, you have to, this actually has some meaning, that maybe there's some homological mirror symmetry or some extra, that it actually implies something about the global symplectic geometry of MR that you have to do more work. But this is the construction. Okay, I should stop here. So
okay, thank you. Are there any questions?
Maybe I lost everyone.
No, there are at least 17 participants, which I can see. No. Can you repeat again your way to see this wall crossing symplectically?
Yeah, so I didn't actually tell you how to prove it, right? Just so let me go there, and then you can ask me.
Yeah, you said that you should move something like almost complex.
So,
yeah,
okay,
but...
so let me tell you how, like, formally how it appears. So now I want to look at the relative symplectic cohomology of this subset of M1. Okay? And so I know that I can embed M0 into M1 such that it contains this P in its image by moving this guy to the right. By doing this, this is a particular case of these embeddings where I have to kind of, exhaust M0 and then move the array a little, do a movement of worms, embed some portion of it, move it more, embed a bigger portion of it, etc. Okay, so that tells me that for this particular embedding of M0, I obtain an isomorphism using my locality result. Using the locality result that I mentioned. So I can see this as a subset of M0, which is just T star T2. And it's not just a subset, it's also a subset that's kind of preimage of a polygon under the Lagrangian fibration of T star T2. And this one, we had shown, I had told you before that this is isomorphic to this convergent power series.
Oh, yes? Yeah, okay, and when you move,
and I move it in the other direction, then I get another identification.
Yes,
and these identifications are not naive. The isomorphism that's induced between them is not monomial.
Yeah, it's a bit strange. Yeah. More questions? So the basic example which one should keep in mind, sort of, I don't know, because for cluster varieties there are plenty of them, yeah.
So I had this picture, maybe this picture. So one symplectic manifold you can construct this way is the CP2 minus elliptic curve.
With symplectic form which has
so
all order 1?
It's the imaginary part. So you can, CP2 minus elliptic curve with this with the complex structure induced from being CP2 minus elliptic curve is not a cluster variety, but it's diffeomorphic to a cluster variety.
Yeah, but in holomorphic terms, you can make it. It's a holomorphic symplectic manifold. You have the symplectic form which has a pole of order 1 on your elliptic curve.
Yeah, so I think that's, if I want Yeah, I didn't think exactly how it relates to that, but I don't think I'm taking the imaginary part of that form.
Okay, so you want it to be a cluster variety, and then you take the
imaginary part, I think, at least. But I mean, of course, to me, I'm just defining the symplectic structure using this diagram representation.
Yeah. I'm a bit confused that the indeed imaginary part of the symplectic form on C star square, for example, is not compatible with the symplectic form on T star to the two-dimensional torus. So yeah, it's a bit different.
No, it's interesting because it's not so. There is another, so there's kind of two standard forms in T star T2, depending on which coordinates you choose. So if you represent T star T2 as like a T star S1 times T star S1,
yes,
and you can write down the symplectic form that's kind of the product of that. So that's one. But you can also choose kind of the S1 of the first component and the R of the second component, and R of the first component and S1 of the second component.
Yeah,
so it's one of them. So there's like two standard ones in the hyperkähler picture.
Okay, so but I interrupted you. You take the CP2 minus elliptic curve.
Yeah, so the mirror of this, so I think that the mirror of this should be this cluster variety itself, that it's diffeomorphic to it.
Yes.
And this, like one thing you can see, for example, there's this tropical Lagrangian here. And this tropical Lagrangian is mirrored to some kind of analytification of an elliptic curve in the mirror. But once you kind of turn on this deformation, both of these disappear. Anyways, it's just some kind of concrete example that. But so like if you finish all this procedure, that you should be able to kind of really talk about these kind of questions.
Yeah. And when you speak about mirror symmetry, you also take into account some behavior at infinity, which is okay.
Yeah. So this I'm not. Yeah. So that's we're not doing some kind of. Okay. So the answer to that, if you want to consider the algebraic version of the mirror, the global invariants of the algebraic mirror, like functions, for example, what will they be in the A side? Well, there you have to construct some kind of Viterbo type symplectic cohomology. But these guys are not exact, or these not necessarily exact, or not necessarily, they don't have contact boundary. But they do have this kind of size determined by integral affine coordinates. So you can again take this kind of, we never wrote this down, so I'm just speculating. But you can again kind of take some linear but with irrational slopes kind of Hamiltonians and kind of take colimit over those and not make a completion. Just like you would do in the
and that will be your symplectic. Okay, all right. More questions? Okay, people are silent. Maybe everything is clear, or or I don't know. But anyway, Umut, thank you for your talk. It's very, very interesting. And your notes will be posted. Lina knows where. Maybe they're already posted. So people who kind of want to more details, they can read them. All right, thank you.
Thank you very much.
So yeah, finishing.